Fine then. Okay. Just let me take out the slides for that. So that whatever I told you when I tell you about how the USRP works is typically not done in a normal USRP training unless you have USRP FPGA training. They don't take it, but I thought this will be a good way for you to understand how communication exactly happens. So a lot of this has to do with how an FPGA is and an FPGA works, especially in a LabVIEW environment. So LabVIEW has something called as LabVIEW FPGA, where we code a lot of things in different ways. So LabVIEW coding is actually pretty different from your LabVIEW FPGA coding. You have to learn more things in an FPGA because you need to do a lot of synchronization processes, etc., etc. Right. Okay. So now, let's say you want to be able to communicate. Hello, am I audible? Ma'am, I'm audible, right? Okay, okay. Right. So let's say you want to communicate with your USRP that's there. So the layering, like I said before, is right. So in a USRP, the layering, like I said, is you have a PC. You are connected from the PC through some sort of interface. After that, immediately you have an FPGA, and then you have your RF circuitry, whatever is there. Now, when you talk about communicating with an FPGA, when you talk about communicating with the USRP itself, there are many things that you might want to communicate. Now, communication can either be my actual signal. So if I want to transmit a sinusoidal signal, my communication might actually be the data points in the signal. Whatever digitized data points are there, I might actually want to communicate it. Now, maybe I want to not communicate this, but just tell the FPGA to set my carrier frequency FC at say 1 gigahertz. Or maybe I want to tell it to set the gain to say 10 dB. One more piece of information, the USRP is an uncalibrated piece of hardware. So when you buy a USRP from NI, they do not calibrate the power and give to you, which is why I'm mentioning that the unit is dB and not the absolute unit dBm. There are companies that will calibrate a USRP and give to you. There is basically an EEPROM that's sitting inside over here, electronically erasable programmable ROM. Over there, when they calibrate it, you will get the unit of dBm. So once the calibration is done, you can actually have the absolute unit. But when NI gives it to you, it will be only in the dB format. You can't, unless you sit and calibrate it yourself or have someone calibrate it for you, everything is in your your relative units. Okay, so let's say I want to, this is one type of information that I can send where my data's size is not very high. So if I want to tell my USRP to set the carrier frequency, obviously this is all I have to tell it. Meaning the size of my data is very small during communication. But say I want to send a large signal to my USRP from my system, then obviously the volume of data that is there is pretty high. This, whatever I'm showing you right now, is something that the user can easily change in the UI during the program runtime itself. In some cases, you can easily change this data during the program runtime itself, small amounts of data that you give, or in fact, even take back from the USRP. Your channel is usually like this. It's a duplex one, or rather at least a half duplex one. You give and take such formats of data. So since one of them, the data size is smaller and the other one has a larger volume, there are two ways in which we send and receive data from a USRP. One of them is called as an MMRA. Now I'll show you, there's actually a animation in this. So the thing is, since if you have lower amounts of data that you want to send and receive, you can actually allow your CPU to come into the picture. Now your CPU is something that deals with a lot of processes. Like I showed you the other day, it deals with a lot of things at the same time. Even if you have 12, 15, 32 cores, your CPU will still, your applications will still be fighting for CPU resources. When you have something that is a very small piece of data, you can afford for the CPU to come into the picture, send in data, like resolve whatever data has to be sent to, resolve all of those issues, and then go out. So if I want to read a U32 data bit, say, which is a very small amount of values, just 32 bits that I want to read, I can basically have it like this. CPU will send to the memory controller. Memory controller will send from the bus, depending on what bus you're using, it will send it to that bus, and then finally to the, your yellow, whatever you're seeing is your target, your USRP. And data goes from memory controller to your CPU back again. And then from CPU, you can see the red part that is there on the left is your memory. So it is CPU, memory, bus, and memory controller. So MMRA, since we use small amount of data, it can afford to do this. But let's say I want to send a signal, and since you already might know, an FPGA is a device that runs extremely fast. If you want to try to do the same MMRA thing for a signal, what will happen is your CPU will be lagging a lot. There will be no point in you having an FPGA because your CPU is simply not able to give your information to the FPGA fast enough. So what you do in that case is, obviously an MMRA reading and writing is definitely not a feasible one. We go for something called as a DMA FIFO. This is something that runs, this is a memory or rather a data transfer mechanism which runs without CPU involvement. So what happens is, in the beginning, the CPU tells the memory controller that, okay, fine, it'll program the memory controller saying, take a lot of data from the memory, from where to where you're supposed to take, and then send it to the this thing that's there, your USRP that's there. Or rather read, in this case read, fine. So you take the data from the USRP, it goes to the memory controller, and since the memory controller is already programmed by your CPU, it doesn't go back to the CPU. It doesn't go back to the CPU, it comes directly to the memory. Since you don't have CPU involvement, the data transfer is actually pretty fast right now. Okay, before I go on to that point, so that is the basic of how a DMA FIFO works. Now inside your USRP's FPGA itself, you have a buffer which we call as FIFO. And in your computer also, you have a software buffer. So what happens is, your USRP gets the data from the antenna, processes it, it starts filling up this FIFO, and simultaneously it starts sending data to your buffer over here in your computer. Your computer buffer starts getting filled up in the RAM, and then if you want it to display it to you, it will display it to you in any necessary format that you want. You want to see the signal, it will show you, depending on how you program it, that is. You want to see the signal, it will show you. You want to see the constellation, you can do that, anything that you want. Now, again, you might think that, by the way, this is in a memory location. Typically the RAM, because RAM, one, it has good amount of memory compared to things like caches and registers. And Two, it has things like, it's able to do it a little faster than your typical hard drives. Your magnetic based hard drives are actually pretty slow compared to your RAM, which is why it takes it into the RAM and then it takes it out of the RAM at a different point in time. Depending on how you've coded it, all of this happens. Now you can think that a FIFO in a USRP's FPGA will obviously get filled up much faster than what your buffer is able to process. So how do we make sure that, and also the problem is that in a FPGA, the FIFO, if it is filled, then there is a condition called as overflow. And if the overflow condition comes, you can understand that you've actually lost some data in the transmission between here and here, because the FIFO does not have any more space to take any data over here from whatever is coming from the antenna. Meaning, so let's say I'm typing A, B, C, and I'm doing this at a very fast rate. If your computer's buffer is not fast enough, what will happen is this FIFO's buffer gets filled up, and then there is a very good chance that we will lose C. So if I transmit A, B, C, I might actually only get A and B. And this is not something that we want to happen. We want it to happen. So what they have done in this case is, and obviously since the USRP's FPGA is much faster, you have to find some workaround in order to make sure that the buffers don't overflow. So what they have done in this case is, when you take data from a FPGA and put it inside the FPGA buffer, you do it one unit at a time. When I say unit, it can be either a sample or a symbol or whatever bit or whatever you want to call it, you can call it. You put in one unit at a time. So let's say I'm putting this inside a while loop. Every iteration of the while loop, I will only add one element to this. Whereas on my host PC, from the RAM buffer that's there, I will take 10,000 units at a time. If you do a basic math, of course, there's a lot of other buffering concepts that will allow your system to run slower. But even if you do basic math, you will understand that the system can afford to run 10,000 times slower than your FPGA without causing any buffer overflows. Is this part clear? This is how we make sure that, because even though the speeds in the FPGA and your system are different, because of the volume of data that we take for every iteration, we're able to make sure that, meaning if, so in an FPGA, let's say a while loop runs 10,000 times. That's the same thing as a while loop in your host system running once. It can afford to be this slow. Any doubts up until this point? Please let me know. Yeah, please tell me. On the system. Okay, so whatever I showed you, so let me talk in with perspective, not to LabVIEW FPGA, but let me just do from what I did right now. It will not do anything because we as a user want to control what's happening, right? The point of an SDR is that we as users want total control over the signal processing mechanisms that are there. So in the codes that I showed you, the Mimo, CISO, and the OFDM codes, it will simply take the data from the antenna, it will convert it into a digital format, and then it will send it to our system. It is raw data, it doesn't do anything. If you do any FPGA coding inside the FPGA, let's say you do matched filtering inside the FPGA, then whatever data that comes out over here will be matched filter. We don't have to do it again. But this is only in the case where we program it on the FPGA. If we don't program anything on the FPGA and just leave the whatever program is already there, it will not do anything. It's just raw data. I hope that I answered your question. Yeah. Okay, so to show you a visual representation, this might be a little hard to understand at first. I get it, because LabVIEW FPGA is something that we learn only when a person has a lot of LabVIEW experience. So it's okay if this is a little confusing. I'll just show you a small animation that will help you understand. So what you see on the left is an FPGA. This is an FPGA. You actually place it inside your computer and then you plug it to your USRP system. And then this is a PXI chassis. I'll come to what this is. But for now, just think that this is your normal typical laptop or your desktop. Now, when I want to read from a DMA device, you see the FIFO gets filled only one by one, but the buffer takes it in bulk. It's taking 4 at a time. You have something called as a DMA engine that will allow you to, that will do all of the necessary communication processes between the FPGA and the system. That is something that we don't have to break our heads on. Point by point write operation is done over here, and buffer bulk read operation is done over here. This is how a DMA FIFO works. That is it with respect to this. The rest of it are complicated FPGA processes. I don't want to take you through this. It's all very LabVIEW specific. Now, one last thing that I want to talk about with respect to how data is sent is this. Now, let's say I have a signal like this. Again, a sinusoidal signal.
Hello, Raghavendra. Hello.
Hello.
Hello, Raghavendra. You have joined
Yeah,
back?
sorry.
Okay,
Yeah, I'm sorry, ma'am. My power went off.
it's okay. Please.
Sorry about that. Okay. I won't be able to send the exact same thing because my computer is not capable of generating an analog signal. So what I do is I discretize this before I send it to my USRP. So let's say it looks like this. Now you can see that each of these samples has a particular time period that is associated with it. So this sample is at T naught, this sample is at T1, this is at T2, so on and so forth. Now, if you remember, I mentioned that we do something called as an IQ rate, where we tell the USRP the rate of samples, the rate at which we send out samples from your this thing, from your system or from the USRP. Now, if I have to consider the rate of the samples, I also have to consider at what rate I am receiving this signal. So obviously, if I have a sine wave like this and I don't specify the rate, the FPGA will not understand at what rate it's supposed to put these samples next to each other. So instead of getting a signal like this, I might actually end up getting a signal like this, which is again not favorable. So what I have to do is I have to mention the time instances as well. So if I have to do this, what will happen is I will not only have to send the magnitude value for each of the sample, I will have to send the time period also. So if I make an array of what I have to send to the USRP, it will be y value and its corresponding t value. So if I say 0, this will be at 0.0. If I say 1, it will be 0.1. If I say 0.7, this will be at time instant 0.2, so on and so forth. Now, it's not a problem as such, but you see that we are unnecessarily sending. So if I have X amount of samples, I'm actually having to send 2x amount of data, which is again not very, it's not very feasible. It's not encouraged because who would want to send more samples from your laptop to your USRP? It's just a waste of time and your resources, right? So but we absolutely have to send this timing information. So a workaround that they have done for this is when you look at a signal, a discretized format of a signal, the distance or the time period between two samples is always constant between any two samples that you take for a signal. So if regardless of if I take it here or here or here, it will definitely be dt. And I can also know when my signal is starting. So let's call that initial point as t naught. So I know when my initial signal is starting, and I know the distance between, or rather the time period between each sample. So instead of sending two arrays of data, what I send is y. Of course, I'll have to send whatever amplitude data is there. There's no going around for this. But for timing information, instead of sending a separate array, I send t naught, which is the original time, and then I send dt, which is my period or space between two samples. So now instead of sending 2x data, I'm simply sending x plus 2, which is much lesser compared to the original approach that we took. This is how we typically communicate with the USRP, by sending in t naught and dt instead of the actual times like this, at what time each sample is in. The USRP will be able to extrapolate where each sample is coming from. So if it is sample number 1, the USRP understands that it is at t naught. If it is sample number 2, USRP understands that it is t naught plus dt. Sample number 3, t naught plus 2 dt, so on and so forth. It can, FPGA can do this calculation on its own. We don't have to do anything. And since it's pretty fast, this is a small calculation only. It can do it pretty well. So this is how we send a signal from the computer system to your USRP. Any doubts in this point? Hello, am I audible? Okay. Yeah, sorry, you had any doubts? Yes. Mhm. I'm sorry, can you repeat that? The minimum bandwidth is the minimum of TX bandwidth, USRP, and host. Okay, transmission bandwidth, as in which one are you referring to? Because these two I understood. What do you mean by transmission bandwidth? You mean the LPF that we have over there in the USRP? Okay, I'll clarify what this is. So you have a computer system over here. Let's say it's the best computer that you can possibly get your hands on. Let's say i9 9th gen, where the processing power is just insane. And then you have your USRP, that you have a low pass filter, analog low pass filter that is there. Let's say it's capped out at 20 megahertz. Okay. In this scenario, so let's say my computer is capable of generating up to 100 mega samples per second. It's capable of doing this. Let's just assume 100 mega samples per second. Now, in the USRP, so since the this thing, what is it? Computer is capable of generating this much, that much data I can send over here. But since the analog bandwidth of this is restricted, and there is a reason why there is this restriction, I'll tell you why. It can only transmit a maximum of 20 megahertz. Right. So in our case, there are only two that I can think of: USRP analog bandwidth and your host bandwidth. Your host is right now is 100, and this right now is 20. So minimum of that, it will be only capable of transmitting 20. Now, in the case of your, let's say you have a very poor i3 system, which is only capable of transmitting 1 mega sample per second. Then your output, even though it's 20 megahertz, the low pass filter itself takes 20 megahertz. The actual bandwidth that you get out here is only be 1 megahertz. Was this your doubt? Okay. Mhm. Mhm. Yes, that depends. So if your USRP is a Rio, then it has a PCIe port that it has. 1 second, let me see that slide is there. It's not in this, it's at the back. If it is a hostel USRP like this with an Ethernet one, then your transmission and reception from host to USRP, the communication will happen through Ethernet. If it is a Rio device, then usually we use a PCIe cable. It depends on what type of USRP you have. But PCIe usually has higher bandwidths, like the speed that you can send in the cable is much higher. Right. Right. So all that will be possible only in your Ethernet cables won't be able to do that. You're right. Only using your PCIe cables you will be able to do that. 100 was just a theoretical number that I gave. I don't. Mhm. Mhm. Right. I'm sorry, what source? You can change the IQ rate. So there is something called as an IQ rate over here. Let me see. You see this, right, IQ rate. Depending on this, you will be able to change what rate you're setting. What was your second question? Sorry, I didn't understand that one. Right, correct. Mhm. Okay. Okay. Wait, host sampling as in, okay, so in the host, okay, I think I got what you're trying to say. Are you mentioning regarding this, what I mentioned, the samples here? These samples? Okay, so this, okay. Right. Okay, I understand what you're asking. So this, whatever I showed you here, is happening inside your computer itself. It's happening inside your PC system, your GPOS system. After this, once it goes to the USRP, once it goes inside over here, just before this low pass filter stage, you have a DAC which converts it into a analog waveform. But the actual process of me generating the wave, this will happen inside the PC. This discretization, whatever is there, samples are there. This happens inside the PC itself. Not necessary, sir, because I am not so I am generating, so I'm writing a piece of computer code and that is generating my samples like this. I'm not taking a signal from the outside world, giving it to my computer and then generating this. I'm not doing that at this point. I am writing a piece of code. So over here, if I show you the code here, sorry, this is the receiver. My data's origin is from this. We call this as a string control. We'll basically be able to write stuff on this. My data origin is not from an analog outside world source. It is within the computer itself. Yeah. So what you said. Yes, so that time what you'll have to do is you will have to, that probably won't affect the way that you do all of this, like whatever RF signal processing that you do, it won't affect, but you will have to send the information in the receiver to your receiver. So let's say you write your audio file at 44 kilohertz. Oh yeah, actually this data you will have to give to your USRP. You're right. This 44 kilohertz information, DT information, you will have to give to your USRP. So in that case, it will be there also it will be relevant. Okay. Okay. So we are done with this. I'll just quickly go through what a PXI system is and what we use it for, how we use it. Suppose since we only have 15 minutes, are there any doubts apart from like what was asked? Anything else that you have? Anything at all? Because if I'm not able to cover it now, I'll be taking a portion of Nirupal sir's portion part actually. The first hour I'll be taking on PXI systems and something called as a radar target simulator. That is again a product by NI, which will allow you to simulate a radar target. I'll do the in-depth thing of that tomorrow after Murthy's session. Post which Nilupal sir will be coming and taking his session on 5G opportunities. Whatever, suppose I'm not able to cover something here, I'll cover it in that session. Is there any other doubts, anything, any clarifications that you require from this at this point of time? Okay, if not, I'll just go ahead to explain what a PXI system is. Okay, so I'm going to take the example of data acquisition for now, because that might make more sense at the beginning stages, but I'll tell you how this applies to RF as well. Now, let's say I am part of your university and I wanted to do an experiment which involves, say, temperature sensor, like a thermostat, and accelerometer. Now, NI gives you a data. NI has something called as DAC cards, which stands for data acquisition. So your temperature as well as your accelerometer values are all analog. So you have DACs that are capable of receiving analog signals, that is analog input DACs. You have analog output DACs. You have something called as digital input DACs, which takes in data in the form of 0, 1, basically digital. And then you have digital output DACs. Now you have, so when I want to do a temperature and an accelerometer, I'll obviously need an analog input DAC, because there is nothing that goes from the data acquisition device to your sensor. It is always from sensor to data acquisition device. Now, why do we need a DAC is because most of us would want to do our signal processings not on an embedded system, but rather initially at least, we would want to do that on a computer system. Now, an easy way to do it would be to use an Arduino, because one, the language is pretty simple, the hardware is open source, so you get it for cheap from a lot of vendors. You then get this thing also. Your development environment, the IDE, Arduino IDE is also free. But the problem with Arduino is a couple of things. Firstly, Arduino is not capable of giving analog outputs. If you want to get anything remotely close to an analog output, you will have to do a PWM. You can only take in 6 analog inputs. You are restricted in the number of analog inputs that you can take. The ADC in an Arduino is a 10-bit ADC. If you are doing it for tinkering purposes, this might be good, but if you want higher levels of precision, you can't get that in an Arduino. So what we do instead is, and interfacing also, it's easy with Arduino, but Raspberry Pi interfacing is actually pretty difficult. You'll have to code on the embedded system. You can't do the coding on your own general purpose system. It's a Linux platform that's usually used on a Raspberry Pi, so not many people are comfortable with it and all of that. So in order to get around all of this, and if you look at your computer system, you don't have any ports that will take in analog inputs or give out digital inputs. You only have things like USB ports. Maybe you have an RJ45 Ethernet port. You may have a Thunderbolt C type port, all of that. So what a DAC does is, it will take the information from your sensors, it will convert it into a format that can be sent on, say, a USB protocol. And your computer has a set of drivers that will talk to this DAC, and it will allow us to take in information when necessary. And then if it is, suppose, let's say in the case of a analog input, we only need to take in information. There is no giving out information that is there. So only this type of communication happens. Suppose you have an analog output system, then you can also give information to this, which is why we need something called as a DAC card. Now what happens is, your computer systems, in especially the laptops that come now, desktops, of course, you have a lot of USB ports, but especially the laptops that come now, you either have 1 or a maximum of 2 USB ports. So let's say I'm trying to do some research on how a sensor network would work. So let's say I have 10 temperature sensors, so on, and then 3 accelerometers. Now, obviously, one DAC card will not be enough, because usually DAC cards either have 4 or 8 slots. Obviously, for these many, you will need multiple DAC cards. If you are doing a large sensor network, what happens is, you will lose the number of, you will not have enough number of ports on your computer system in order to facilitate the input from all of this. One. Second one, if you take data from different USB ports, you cannot guarantee the synchronization of the data that is there. The data is not synchronous. So let's say I've actually seen people do this project. There's apparently a road where you have a temperature sensor and an accelerometer, and they try to do some machine learning process on this depending on the whatever is there. Now it is crucial, especially if you have sensitive things like machine learning, that temperature data, let's say I want to take data at T naught, temperature and accelerometer. If I want to take this data and then measure what is the T naught value for temperature and accelerometer and then do some machine learning processes on this, it is crucial that both temperature and this whatever accelerometer value are taken out at the same point of time. If it is the same USB port, then you can actually be sure of this. If there are different USB ports, then there is a chance that this gets taken out as T naught plus delta T. So what happens here is your data is not perfectly synchronized, meaning the model that you are doing in a machine learning, I'm taking machine learning for an example, the machine learning model that you do is not accurate. So you have all of these issues that come into picture when you have a larger system of sensors that you have or larger number of data cards that you have. So what we do is, what NI has done is, they have made it in such a way that usually your data acquisition cards, most data acquisition cards, again, not all of them, but most data acquisition cards don't directly interface with the computer. This doesn't happen. What they do is they go into something called as a chassis. So a chassis will look something like this. A chassis is nothing but, so it will have some sort of, usually what you see is a VGA port over here, or something that looks like a VGA port at least. A chassis will have multiple slots with the VGA ports that are there over here. What you do is you take this data card, you insert it into the slot and connect it with whatever interface is there over here. So let's say in the university, I am working on temperature and accelerometer, but someone else wants to work on digital interface. You don't need to worry. All of the data acquisition, or rather most of the data acquisition cards are of similar size and they have the same interface, the same VGA type interface. So if I am working on something, I can put my DAC over here and work on it in the chassis. And let's say someone else from your university is working on something else, they can remove mine and they can put in their NI card over here, data acquisition card, and it will still work. Of course, your code will have to change. The code that you use will have to change, but the actual physical interface will not change. Now I can have multiple such cards embedded in my chassis. Again, chassis also has different things. You can have different number of slots that are there for a chassis. There are 4 slot, 8 slot, 16 slot, depending on your application, you can purchase it, and the price also varies accordingly. So the advantage is that you have only one interface connecting the chassis with your computer. So even if you have, say, 16 sensors, and in this case, you might require actually 2 USB ports if you're only using the data acquisition cards. What they do is if you put it inside a chassis, all the 16 sensors data will be synchronized and it will come to your PC. And you will be able to access more and more data acquisition devices than you would be if you would just use a computer system. If you want me to show you a picture of that, I can. 900. Okay, so this is something called as a stereo chassis. You don't need to understand what exactly it does, but you can see the slots inside, right? This will be a better one. You see the slots inside? These are where we will connect our data acquisition cards. You have multiple slots. Depending on the model that you have a number of slots. And the data card itself will look like this. So this is a, if I'm not wrong, digital input output card. So it will look like this, where you will connect your digital inputs and outputs over here. Behind this, you will actually have, you see this, I don't know if it's very visible, but this is what will connect to your chassis port over here. Just connect this, you can connect multiple of these over here, and all of them are synchronized. So in that way, you will be able to use chassis. Now, the reason why I'm telling you this is because you can do this for RF systems as well. So let's say you want to have a 8x8 MIMO setup. Let's just assume that you want to do this. Now, the thing is, when you want to do an 8x8 MIMO system on the same, you will obviously have to get all of the data on the same computer. Now, if you look at, okay, so we were talking about, sir was also asking about a PCIe system, right? If anybody who doesn't know what a PCIe system is, that's fine. It's a data communication protocol that's present. You have different keyboards especially for that. It's a data communication protocol. It's a serial data communication protocol, which actually has very high data rates that are present. How do you might not have seen a PCIe port on your desktop or laptop simply because it's not present on the outside. Most of your CPUs will have them. So if you just open your CPU, you will find a PCIe slot. You will basically find something that is very long like this, a port that's very long like this. Ma'am, can I extend the session for just 5 minutes? Is that okay? Hello. Am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Yeah. Is it okay if I extend the session for just 5 minutes? I'm almost done. Okay. I'll just take a few minutes. So if you will find a slot like this, you can show it to you again over here. See, slot. On your motherboard, you will find slots like these. In a normal desktop, the number of slots that are there are limited. You will only probably be able to have one USRP Rio per system. If yours is a workstation, probably it will have more. But if it's a general PC, your motherboard will only have one of these. So it is difficult to interface that many USRPs within one, especially if it's a USRP Rio. If you want to do an 8x8 system, then on a system, it's usually not possible. So what we do is we also have data acquisition chassis are also there. You also have RF chassis where you have PCIe, something called as MXI cards over here, which is, you can think of those as similar to your data acquisition cards that I mentioned. These cards on a chassis, they will be placed inside a chassis, and they will have your PCIe ports that are there. Now, there are chassis where you can actually put 4 USRPs at a time. And since you're putting 4 of them, you can actually achieve an 8x8 system. Since they're Rios, they have 2 RF channels, you'll be able to achieve an 8x8 Rio systems. 8x8 MIMO systems. There is another reason. This is just a very rudimentary and fundamental reason to have a chassis. There are actually more that is involved in this. I will be explaining more of this. So tomorrow in Nilpal session, I will be taking, like I said, I'll be taking just 1 hour in the beginning, post which he will be taking about 5G research opportunities. So in that point of time, I will tell you the other advantages with respect to a chassis. There are things like you can do triggering mechanisms inside hardware triggers that are required over here. And you can also do something called as daisy chaining with your reference clocks. It might seem like gibberish to you, but I'll explain all of this in detail in the next session. So that concludes my session for today. I'll continue this in the next session. Anybody has any doubts regarding what I did, anything in today's or what Ajay did or my last session? Anything at all?
Yes, Raghavendra, thank you. I think the participants are very clear with the things. Okay. So, yeah, thank you so much, Raghavendra. I think Nilutpal was telling me about the change in the schedule tomorrow. Okay. Yes. Dear participants, we'll assemble back at 1:30 for the next session by Dr. Surinder Yam from NIT Puducherry. As I mentioned, he'll be talking on the technologies for the 5G and beyond wireless communication, a physical layer perspective. So now we'll break for lunch. Thank you.
Thank you, ma'am. Thank you, everybody.
Thank you, Raghavendra. Thank you.